in an experiment.
And we don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This time, tiny devices that fly using the sun's heat.
And is gravity quantum? I'm Shamini Bundell.
And I'm Nick Petrichow. First up on the show, researchers have created a device that can fly just by using sunlight. But this isn't a solar-powered vehicle in the manner you may be thinking of. Instead of using solar panels to create electricity, this vehicle exploits sunlight's heat to levitate in the air. And the team behind it think it could be used to study a mysterious part of the Earth's atmosphere, or even help explore Mars. Rather than using propellers or engines, this craft, just 1 centimetre across, exploits a phenomenon known as thermal transpiration.
Thermal transpiration describes the flow of gas at low pressures from a region that is cold to a region that is hot. Typically, that's a little counterintuitive, right? We're used to thinking of things moving from hot to cold. But when you're at low pressures, things get a little wonky.
This is Ben Schafer, one of the team behind the new device.
It's actually like a density-driven flow. The cold area is more dense than the hot area of gas. And so that density difference causes the movement of air. And so the structures that we've made, because they're hot on one side, it causes air to flow around them. And in the cases of our structures, through little holes, that pushes the structure upward.
Thermal transpiration has been known about for a long time. In the 1870s, a device known as a crux radiometer was invented that exploited this phenomenon to allow a little weather vane-like apparatus inside an airtight bulb to spin around when light was shone on it. For a decade, Victorian scientists tried to figure out how it worked before landing on thermal transpiration. For a long time, though, this phenomenon has just been a simple curiosity. Even in modern times, it's been hard to make materials that are light enough to exploit thermal transpiration for flight. Even then, it would only really work in low densities of air. These were challenges that Ben and the team were curious to see if they could overcome by using state-of-the-art nano-engineering. The team used a variety of techniques to create a lightweight sandwich of 2 perforated membranes separated by tiny pillars, with the bottom membrane designed to absorb more heat than the top. And this design seemed to be key to generating the lift the team needed to get their craft off the ground.
Because it's those membranes that create this temperature difference. The top membrane, when illuminated, stays cool, but the bottom membrane stays hot. And the way that we do that is we coat the bottom membrane with a layer of chromium, which is very absorptive to things like sunlight. And that causes this airflow both around the sides of the structure and through these perforations in the membranes that causes the entire structure to lift up.
As light shone on this 1 centimetre sandwich, the chromium bottom heated up, dragging cold air down through the holes and generating lift, allowing the device to levitate. Ben and the team did some tests on the ground to show what levels of light intensity are needed to get the device to fly. Based on this, they used computers to model how a 6 centimetre wide circular version of their device would fly in a thin layer of the atmosphere known as the mesosphere, some 50 to 80 kilometres above the ground. The team's models suggest that it would be able to fly well in this layer of the atmosphere and may even be able to carry little loads.
We found that, at least during the day, you could loft hundreds of milligrams of a payload. And that doesn't sound like a lot, but nanofabrication and microscale devices have gotten so good in recent decades that is enough weight that you could put small atmospheric sensing hardware or like a telecommunications package on board these structures and have them fly around the upper atmosphere. So you could collect things like wind, pressure, temperature data. All of that is important to climate modeling.
These data could be key to help researchers understand more about the mysterious mesosphere, a part of the atmosphere also referred to as the ignorosphere, because it has been notoriously difficult to study. This is, in part, because the air there is too thin for aircraft and balloons, but too thick for satellites. And even away from Earth, they think their device could even help with exploring other planets.
So we did some modeling of how well these things would fly on Mars, and it turns out that they would have pretty comparable performance to how they would act on Earth. And so you could do the same applications in the Martian atmosphere, and because these devices are so lightweight, it wouldn't be terribly costly to send a rocket with these devices out to Mars. And obviously that's kind of a blue sky idea way down the line, but the physics says it works.
Now, a major drawback of any such device is that they only really fly for as long as the sun is around, making nighttime flying tricky. But these devices could be useful in the summer in high latitudes, where there are periods of 24-hour sunshine for weeks at a time. And if the device is not carrying any loads, Ben thinks it could potentially stay aloft even without the sun, as it could exploit the Earth's thermal infrared radiation.
For passive devices or small devices, they could stay aloft overnight and potentially last weeks or months, depending on what the winds in the mesosphere look like.
Now, Ben's isn't the first successful attempt at flight using this technique, although previously it's only been achieved by using light intensities much greater than that of natural sunlight. The new device can levitate in 55% of sunlight's intensity. But there's still more work to be done, and some practical testing needs to take place in the mesosphere before these devices are ready for prime time. Ben is looking into if there are designs that could allow them to fly when there's less sun available, and exploring how they could be used to carry different technology. For now though, this research is a step towards making useful devices from what was once a Victorian curiosity.
The most exciting thing about this paper for me is the fact that we took some really obscure piece of physics and translated it to something that has real-world applicability, showing that these devices could actually fly and benefit people from their use in the upper atmosphere is really profound to me. And I think I'm thrilled nanofabrication's gotten so good that we can actually start making things that are useful.
That was Ben Schafer from Harvard University in the US. This piece was written and produced by me, with reporting by Dan Fox. For more on this story, check out the show notes for some links.
Coming up, we'll be hearing about why it is that quantum physics and gravity have been so hard to reconcile. Right now, though, it's time for the research highlights with Katrina Clark.
The Pazyurek people, who lived in Siberia more than 2,000 years ago, are known for their intricate tattoos of animals. Now, a study reveals some of the techniques used by the ancient tattooists who created this body art. A team used a variety of imaging techniques to create a high-resolution 3D image of a female mummy with tattooed hands and forearms. The mummy was found in a tomb encased in a layer of ice, and its skin, with pigment, was preserved. Working with a modern tattooist, the researchers concluded that an ancient artist used a multi-point tool to apply pigment beneath the skin, with finer details added using a single-point instrument. The images also revealed variations in design and execution between some of the tattoos, suggesting that more than one tattooist was involved. If you're inclined, head over to Antiquity to read the paper. In 2013, sea stars along the Pacific coast of North America began dying in huge numbers. Now, scientists have got an idea what caused these marine animals to die off in enormous numbers. A disease known as sea star wasting disease affects dozens of sea star species, and their mass die-off triggered an explosion in the number of sea urchins, which sea stars eat. The boom in urchins, in turn, damaged kelp forests, which urchins eat, up and down the Pacific coast. To pin down a culprit for the disease, researchers compared the genetic profiles of microorganisms found in healthy and infected sunflower sea stars. These animals have succumbed to the disease in their billions. The genomic analysis revealed that sick animals carried a higher load of a particular bacterial species. Injecting these bacteria into healthy sea stars led to them developing the disease, suggesting this microbe is the cause. Read that paper in Nature, Ecology and Evolution.
As we've already covered on the show, this year is quantum mechanics' 100th birthday. But in all this time, there's something that researchers haven't been able to fit into a quantum framework of the universe, and that's gravity. This week, Nature's Davide Castelvecchi has written a feature article looking at efforts to figure out if gravity is, in fact, quantum in nature, something that's had physicists vexed. Davide talked with Benjamin Thompson about the feature and started by giving a quick refresher on why quantum physics has been so successful.
Yeah, so quantum mechanics has been extremely successful in all of its manifestations, including and especially particle physics, where it has developed into what physicists call the standard model of particles and fields, which has been stress tested to the umpteenth decimal point. Some might say it's a victim of its own success because physicists find it frustrating that they haven't been able to find a single experiment that conclusively found something wrong with it. Why is that a problem? It's a problem because the laws that we know cannot be the full story, in particular because they don't seem to even be compatible with what we know about gravity.
A lot of what's known about gravity, of course, comes from Einstein's theories of relativity, that sort of thing. Why has there been a struggle to work out whether gravity may be a quantum phenomena?
Although Einstein's theory is very successful, some might say almost as successful as quantum physics at describing the world, it does so only on the very largest scales, as far as we can see. And the problem is when you try to take a classical equation, one that describes, say, particles as little points of matter that move in a predictable way, and turn it into a quantum theory, you immediately run into problems. So there is like a tried and tested mathematical machinery that physicists have been using since the 1920s that takes a classical equation and turns that equation into one that describes these fuzzy objects of quantum physics that, for example, can be in a superposition of being in two places at the same time. That technique has worked for pretty much anything else, but not for gravity. Because when you try to put Einstein's equations in it, you get nonsensical results.
As you say, Einstein's equations work at very large scales, but quantum is usually focusing on the very small, and it seems like it's been hard to bridge that gap. Why is knowing if gravity has a quantum element something that researchers are keen to find out?
Well, I think most physicists are very uncomfortable with the fact that we have one set of principles that applies to gravity and to cosmology and the expansion of the universe and so on, and another set of principles that applies to elementary particles and light and so on, the microscopic objects. Why should nature have two completely different sets of principles? And it's not just the equations, it's the very basic principles that seem to be inconsistent. Some other physicists would say, well, okay, that's just what it is, and we have to live with it. But others think that there has to be like a more fundamental theory of everything that kind of reconciles this contradiction.
And researchers have been trying to reconcile this for some time then, using various mathematical techniques. What are some of the ones that have been favoured thus far?
Probably the most popular, if you ask theoretical physicists at least, is string theory. Now, string theory does seem to reconcile these two worlds, the microscopic and the macroscopic. And it does so by rebuilding physics from scratch instead of trying to force feed the old equations into quantum physics. What it does is it replaces elementary point-like particles with infinitesimally thin vibrating strings. String theory has led to a lot of interesting developments on the theoretical level. What a lot of physicists find frustrating is that it seems extremely hard to get any concrete predictions out of string theory and to connect it to the real world.
And experimental data on whether gravity is quantum so far has eluded researchers. But in your feature, you're really looking at this kind of new wave of ideas that could actually test this in a lab. And a lot of this seems to do with using that strange quantum phenomenon of entanglement. Maybe you could explain broadly what a lot of these experiments are trying to do.
A lot of the people I talk to agree that what they're trying to do is go back to the basics. Instead of starting from grand ideas, at the very basic level, what these experiments would love to do is check whether gravity is compatible with the basic quantumness of particles. So can objects have this cloud of statistical probabilistic distributions rather than being in a well-defined place at a well-defined time all the time? And in particular, one of the basic requirements of something being quantum is that multiple objects can share a common kind of fuzzy quantum state, which is called an entangled state. So a lot of these experimental proposals are trying to test whether gravity can produce entanglement.
And maybe you can give a sense of how researchers are trying to do that then. There's a variety of different options, but it seems to be getting two very, very small objects very close to each other, is it, pretty much?
Yes, and the challenge is that, like we discussed earlier, quantum physics tends to manifest itself at very small scales for very small objects, but it's very hard to see the gravitational attraction of two very small things. So you want to be able to have objects that are large enough to have a measurable gravitational attraction or interaction, but still be small enough that they have quantum properties.
How are researchers going about trying to test this idea then, that they can see this in action?
One idea is to put two tiny diamond crystals in a vacuum chamber and let them freely fall next to each other, and then see if their mutual gravitational attraction can produce entanglement. And the entanglement would be revealed by the quantum spin of an individual electron in each of the crystals.
So if the spin of these electrons is matched between the two crystals, it suggests that these two things have become entangled, and the only thing that could do that entanglement is the gravity which is being imparted on them as they're dropped.
Yes, so that would reveal that gravity is of a quantum nature. It wouldn't tell us anything specific about what a quantum theory of gravity should look like necessarily, but at least it would be a start.
And these experiments are a little ways away yet. But if the results are positive, then suggesting that entanglement caused by gravity and therefore gravity being quantum do happen, what does that mean then to the world as we know it, I suppose?
For one thing, it means that there's still a lot of work for physicists to do to understand what this quantum gravity is, what this mysterious theory looks like. But there's also another really intriguing possibility, is that the answer is gravity does not have a quantum nature. And it's one of the more revolutionary ideas that have been proposed in recent years, that perhaps gravity is not quantum after all, and we do have a classical phenomena coexisting with the quantum universe.
In that situation then, where I guess the status quo is maintained, that we have these two separate worlds, if that continues, what does that mean for future physics work, do you think?
The consequences could be really far-reaching, because what physicists have been realizing in recent years is that if gravity stays classical, you cannot have that without introducing an element of randomness in gravity itself and in the way it acts. And this element of randomness could help to explain the most mysterious problem in quantum physics itself, which is what happens when you measure a quantum property and you get the roll of the dice that is typical of quantum experiments. It's something that has had physicists scratch their heads for a century. It's called the quantum measurement problem. But intriguingly, solving this problem about gravity could also be a first step towards solving the quantum measurement problem.
You've spoken to a lot of physicists about this, Davide. Where's their money going? What is their sense of whether gravity has a quantum element to it or not?
I think it's fair to say that the majority of physicists still think that quantum physics will prevail and that the fundamental nature of the universe is quantum. And so therefore, there will have to be some quantum theory of gravity as well. But at least people are now reckoning with the fact that this is not a given. And that's what's interesting about this next generation of experiments, because they could finally give us some answers to this problem that has been open for a century.
Davide Castelvecchi there talking with Benjamin Thompson. To read Davide's feature, look out for a link in the show notes.
Finally on the show, it's time for the briefing chat, where we talk about a couple of stories from the Nature Briefing, Nature's daily email roundup of science news. Shamini, what's been happening in the world of science this week?
Yes, so I have been reading all about genetics this week. This was a Nature article based on a Nature paper. And there's some really interesting stuff about how the effect of a gene can vary depending on where you actually inherited that gene from.
Right, and by where you got it from, you mean like which parent or,
Yeah, so exactly. So you've got half your DNA from one parent, half your DNA from the other parent. And, for a lot of genes, I might have skin colour or hair colour that's sort of impacted by both sets of genes. Both alleles are sort of active and making my body a certain way. But there are certain genes where it makes a difference if you inherit it from your female or male parent. And this study is about a new method to identify those genes, which can be kind of tricky to do. And they've identified a load of genes, they've got this new method, and they've also found quite a lot of genes where if you inherit it from your male parent, it has the opposite effect than if you inherit it from your female parent.
That is so bizarre.
which is quite wild. So an example they gave, there's this one particular variant of gene which impacts diabetes. And if you inherit it from your father, it increases the risk of developing type 2 diabetes by 14%. But when inherited from the mother, it decreases the risk of developing type 2 diabetes by 9%. So just complete opposite.
Wow, just when I thought genetics couldn't get any more baffling, because
so
many traits are so complicated and depend on so many different factors, there's yet another factor that it depends on. So how is this working? Like, how does the, body know where these alleles are coming from?
Yeah, so this study doesn't go into it, but, from a bit of background research, this is all developmental stuff, and this is almost certainly about epigenetics. So it's not the DNA sequence itself. During development, you get markers. Maybe it's DNA methylation, maybe it's histone modifications. Those are the sort of well-known ones. But the reason it's been quite hard to study these things and find these things is also because you would generally have to have the offspring's DNA and the two parents' DNA. So the sort of clever thing that this study has done is gotten this statistical method whereby you don't need the parents' DNA, because that's often quite hard to make sure you have access to. It uses data from the UK Biobank, but if you have at least one other relative's data, you can kind of infer the direction of inheritance for any given genetic variant.
So they've got this huge data bank of loads of people's genetics, and they've just been looking at, if you get this gene from this parent, then it has this effect. And if you get this gene from this other parent, it has this effect, that sort of thing.
Yeah, and they found at least 30 parent of origin effects, they call it, in 14 different genes. And that includes 19 of those that had what they call a bipolar effect, i.e., it's an opposite effect depending on which parent it came from.
Crikey.
And another interesting thing was that loads of these genes, almost all of them actually, were related to growth and metabolism in terms of the actual impacts they were having. A lot of them were even on the same chromosome. And that's potentially quite significant as to why this parent of origin effect exists at all.
Oh, how so?
Well, this isn't a study that's sort of looking at the cause, but one of the theories as to why this kind of happens, and this is particularly looked at in placental mammals, is that the mother and father of an offspring kind of have different sort of selection pressures on what they might want from that offspring. So if you're a female parent and you are growing a child within you, you might want to maybe hold back some of your resources for yourself and for any future children that you might have, even at the expense of this particular one. Whereas the male parent doesn't have that extra investment, so the selection pressure would be maximize the fitness of this particular offspring. Now, that's not 100% sort of certain, because there are other animals that also kind of show this effect, but that would explain why a lot of these new findings are in growth and metabolism.
Well, I mean, it certainly sounds like a fascinating insight into how genetics works, but do the researchers think that this could be used for anything? You mentioned like diabetes and things like that. Could it help inform people whether they're more or less susceptible to certain conditions?
Well, they're definitely hoping that their statistical method could be used to find more parent of origin effects in genes. And although it doesn't have a direct sort of immediate medical implication, as with all of the sort of increased information that we have about how our genetics, and in this case maybe epigenetics, impacts us, this is just sort of like more information on the kind of things that could be impacting things like diabetes and other illnesses and conditions.
Well, my story this week is kind of related to that because it's about a potential way to treat Alzheimer's. So this is an article I was reading in Nature based on a Nature paper, and using human brain tissue and mouse studies, they've shown that lithium could be really important and may even be able to reverse some of the symptoms of Alzheimer's disease.
Oh gosh, because am I right in thinking that there's a lot of research on the causes and possible treatments, but there's certainly not anything particularly effective, and it's not currently super well understood. Is that right?
That's right. There are some drugs available, but they mostly work on slowing the progression of Alzheimer's.
Right,
so you may be aware that Alzheimer's, one of the symptoms of it is that you accumulate little protein plaques in your brain. These are not good news. And so what these drugs do is they slow the progression of those plaques. So they build up more slowly, and that prevents Alzheimer's progressing as quickly. In this study, what they've shown, at least in mice, is that with doses of lithium orotate, they've been able to actually reverse some of these effects and restore memory to these mice.
I have many questions, but what is lithium orotate and why were they experimenting with it?
Well, lithium has been known as a mood-altering substance. So it's a metal, but for a long time, it was actually used in an early recipe of 7-Up because it was known to alter people's mood. So it's been known for a long time for this.
Way.
And because of that, it's been used to treat people with bipolar disorder. And what researchers noticed is that when these people with bipolar disorder were taking lithium, their brains aged more slowly. And so there have been clinical trials looking at lithium for this exact reason, but their results have been mixed. So this new study was trying to really understand what's going on here and why the results have been mixed and how is it potentially having this sort of slowing of brain aging effect.
And you mentioned that these experiments were done in mice, so a mouse model of Alzheimer's. How does that relate to human Alzheimer's? What's going on in a human brain potentially?
It's a good question because these findings in mice, they don't always translate into humans. But in this study as well, they looked at human brain tissue. And so they showed in this human brain tissue that had Alzheimer's that in the parts of the brain that were affected by Alzheimer's, there was actually less lithium present. And so that indicates that less lithium leads to more Alzheimer's progression. And so they looked at the mechanism of how this is working as well. And so what happens is the brain's lithium, because it has a supply of lithium regularly, it gets tied up with these protein plaques in the brain. So the lithium gets sort of tangled up and can't be used by the brain. And so it's not available for the essential brain functions it's normally used for. And so that's where the lithium may well be going when people have Alzheimer's, and it just leaves less lithium available for the brain.
So that's a potential mechanism as well. So it's not just sort of, here's a potential treatment. This could be a mechanism by which Alzheimer's is having some of these negative impacts, why these plaques are sort of harming the brain.
Yeah, and it could be why giving people lithium to treat bipolar disorder has had this effect of slowing brain aging. And also in places where there is lithium in the water supply, there are lower levels of dementia. And so this could be the reason behind that. And one of the interesting things is, as well, they may be able to explain the discrepancy that has been shown in clinical trials before. Because I said it has been tried in clinical trials, lithium. And I mentioned that they used in this study lithium orotate, and in the previous clinical trials, they've used lithium carbonate, but it seems like lithium carbonate still gets tangled up by the protein plaques, whereas lithium orotate doesn't. And so that could explain the discrepancy between these clinical trials that weren't showing the effects that have been seen in more serendipitous findings like with bipolar disorder.
That's fascinating. There's so many little tidbits in there that really surprised me. But I suppose this is one of those studies where you go, oh, should we start taking supplements of lithium? Is this the way to stave off dementia?
Well, the first thing to say is they need to do clinical trials of this. They need to understand how this is working in humans and how effective it is. And if you have too much lithium as well, you can get lithium toxicity. They didn't see any lithium toxicity in their study, so that is quite promising, but there'll be a lot more to be done. And that also speaks to one of the difficulties of this, because lithium is just a metal. And as you know, when pharmaceutical companies develop drugs, they patent the drug to pay for the development of it, to make money off that drug.
Yes.
It's unclear whether a pharmaceutical company would want to do this, because you can't patent lithium. So would they want to put the money up for the development? So it's unclear where the funding for this would come from. Maybe from governments, maybe from elsewhere. But on the flip side, lithium is also very cheap. So if this was developed, it could be a very cheap and available way to treat Alzheimer's. But yeah, more studies to be done first.
Wow, that's really fascinating. Well, thank you, Nick, and listeners. If you want more on either of those stories, we're going to be putting links up. They'll be in the show notes, as well as the link to sign up to the Nature Briefing, where you can get more stories just like these, but in your email inbox.
That's all for this week. If you enjoyed the show, let us know. You can leave us a review or a comment on your podcast app of choice, or you can send us an email to podcast@nature.com. We're also on X and Blue Sky as @NaturePodcast. I'm Nick Petrichow.
And I'm Shamini Bandel. Thanks for listening.